Hi, my name is Kent Lee and I teach computer science at Luther College. In this series of videos, I'll be talking about data structures and algorithms with Python, which goes along with the text that I've written with my co-author Steve Hubbard. I would highly encourage you to go out and get this textbook and read it along with watching these videos to get the most from these topics. In Chapter 2 of the text, we begin to study something called computational complexity. This is a term that's used by computer programmers as a measurement of how a program will operate or how a program will execute given data of different sizes. So computational complexity is really an analysis that's done of a program to understand how the amount of time increases as the data size increases. To understand this, we might run experiments and plot those experiments. And in support of this, I've written a program that allows you to plot the time versus data size that computational complexity studies. We can get that from this website, the CS2 Plus website. If you go under the Chapter 2 and Computational Complexity to the Plot Data program, you can download that program here. I'm just going to copy it here, and then I'm going to start up Wing and paste it in. So this program can be run from directly within Wing if we want to. There's really no running of it that is required to be run within Wing here. So I'm actually going to save this program, and I'm going to put it in my Dropbox bin directory so that I've got it for so I can use it at any time I want to. And I'm going to actually call this plot data. And I'm not going to put a .py extension on it so that I can just type plot data when I go to run it. Now it's not going to give me the syntax highlighting within Wing here, but that's okay. To make this program executable, I'm going to get into a terminal window, and I'm going to cd into ~Dropbox bin, and I'm going to do a chmod plus x on plot data. Now that makes it executable so that it can be executed just by running it from the command line. But there's one little thing that we've got to do first. So you need to say which Python 3, and in my case that happens to be this long path here to where Python exists, and I'm going to go ahead and copy that, and then I'm going to bring up Wing here, and I'm going to put that in as the very first line in this program. You actually do !! and then paste in the rest of it there after that. So save that, and now if I want to plot data, I can just say plot should be able to say plot data from anywhere within the system. If I have the Dropbox bin directory in my path, which I do not at the moment, so I'm going to add that into my path. And to do that, I'm going to use some editor. Doesn't matter what you use. And I'm going to go into my ~/.bash rc file, and I'm going to add that Dropbox bin directory into my path. So I happen to have an export path in here. It has a number of other things in it already. What I'm going to add to that path I'm just going to add it actually as a separate line, and you can do the same. So export path equals, and I'm going to leave dot as the first thing, and then I'm going to put in here slash users for myself anyway, slash Lee Kent, slash bin, slash Dropbox, slash bin. You can find out what your path should be if you just cd into Dropbox bin and then type pwd, and you'll see the complete path that you want to add to it. So you can just do a copy there and paste that right in here to make sure that you get it just right, and that's what I've got there. And then you'll always want to add at the end of the path $path there. So once that's all in there, then we can source ~/.bashrc. Next time you sign on, you won't have to do that, so that just takes care of it this time here. And after doing that, then I should be able to just say plot data, and it should start up. So it is starting up the application right now, and this is what the plot data program looks like when you first start it. Okay, so that's all we need to do for the moment with that. I want to take an example and work through an example with you so you can see how this might work. And on the course website, I have an example program that we can work with. That example program is the list access timing program. So we'll download that one as well. In my case, it comes up this way, and I'm just going to go ahead and paste that in here, and we'll click Save to save it. And I'm going to put mine in my Dropbox, classes, and in a directory that's for my course that I'm teaching right now. So we'll call this list access.py. Okay, so let's take a look at this code so we can see what's going on in the list access program. This is a program now that's going to run some experiments on accessing various elements within a list, and the experiment is really to find out whether the length of the list affects the amount of time that it takes to access a random element within the list. So to run this experiment, we're going to write an XML file, and I'm assuming that at this point you've watched one of my videos on XML files and understand a little bit about them. And the first line in an XML file is going to be XML, and so we're going to open a file for writing here. We're going to create a file called listaccesstiming.xml, and this is going to be the first line within it. And then the plot format requires us to give the plot a title, so we're going to create an XML element called plot, and we're going to give it a title here, the average list element access time. So again, the size of the list is going to increase. That's the size of our data. And we're going to find out whether or not it takes increased amount of time to access a random element within the list, given the size of the data. So we're going to build some lists from 1,000 to 200,000 elements. Okay, that's going to be our xmin and our xmax. And we're going to go by 1,000. So we're going to increase the list size by 1,000 each time. And so this for loop is just going to go through building lists of that size. We start out with xlist being empty here, and then we're going to append to xlist. We're going to append the size of the list that we're working with at this point. So xlist is going to keep track of the various sizes of lists that we're working with. Then we're going to actually create a list of that size. So this creates the this creates a list of a bunch of zeros. So the list has got a bunch of zeros, and we're going to create it of whatever size x is. So the first time through it'll be 1,000 elements, and then it'll be 2,000 elements, and it'll move on from there. We're going to sleep for just a moment in this program to let things kind of settle down, and then we're going to start our experiment by getting the start time for this experiment. And we're going to access 1,000 elements within that list. So we're going to do this 1,000 times. We're going to compute an index into the list at random, going from 0 to x minus 1. We'll retrieve the value from it, although we're not going to really do anything with it. We're going to make sure that it looks like we're doing something with it. So we're just going to multiply it times prod, which is 0, so it doesn't really have any effect. But we want to make sure that the Python program doesn't optimize the operation out somehow. So we're going to access the element, and then we're going to use the element to multiply it times prod. After we've done this 1,000 times, we're going to get the end time. So the start time and the end time are in microseconds. So if I subtract the 2, I get the delta t, which is the difference in microseconds between the two. And I can actually, from delta t, I can get the total seconds from it. So there's a delta t is an object that I get back from doing this operation. I can get its total seconds. I multiply that total seconds times 1,000 just to get the microseconds from it then. So, and that will be the total access time for doing 1,000 accesses. So y-list, the vertical axis, is going to be the amount of time it took to do that. So how long does it take to do an access? And actually, microseconds would be 1,000,000 times the seconds. But I'm going to divide by 1,000, so I'm only going to multiply by 1,000 here. So divide by 1,000 for the average access time, but also multiply 1,000,000 for the microseconds, just so you see that that calculation is being done here. So I'll have the average access time for accessing an element in a list of that size. So then I go back around and loop again, and I make the next size, which would be 2,000 to begin with, and I'll do 1,000 accesses in there, and I'll see what's the average access time, and I'll append that to the y list. So when I'm done, again, the x list will have all the sizes of lists that I worked with, and the y list will have the access time in microseconds, the average access time in microseconds for all of those different sizes of lists. Okay, so then I want to go ahead and plot this, and that means that I'm going to go back to the file, and I'm going to write what the two axes are. So the x-axis is going to be the list size, and it's going to go from x-min, which is 1,000, to x-max, which will be the 200,000. And on the y-axis, the minimum will be the min of y-list, so the minimum access time. And the maximum, I've set it to 60 in this case to just make sure that I have a nice looking plot here. So 60 microseconds. And that's the label for each of those. So we have axes, and then we've got both the x-axis and the y-axis, and then we got axes again down here as well. And then I'm going to actually write the sequence of the data. So I'll write the sequence, and I get to specify which color it is, and the title for that sequence, average access time versus list size. And within the sequence, I need to plot all the data points, which is going to be, I want to plot the list size at I. So I is an index within this list. So it's going to be one list size. And then I want to plot its corresponding average access time for accessing elements within the list. Okay. And then I go on after that, I guess, and I'm actually going to do one more plot with this. So this part of the program tests access at 100 random locations within a list of 200 elements to see if it matters where I access an element within the list. So if I've got a list of 200,000 elements, can I access values at the beginning of the list faster than values at the end of the list or not? So that's what this is going to do down here. The list size is already going to be 200,000 here. So the Y list is just going to be 200,000 long then. And so then I'm just going to go into my X list here and increment a value within it. So I'm just doing 100 random locations within the list, so that my index is going to be in the range from 0 to 200,000 minus 1. I access that value, add 1 to it. I get the start time before I do this and the end time afterwards. And the delta t again is the end time minus the start time. And then in the Y list, I'm just going to go ahead and add that to the total number of seconds times a million there, so that I get the microseconds again that it took to access an element at that location. Okay, and this keeps track of how many times I accessed that location. So just in case I end up accessing an element more than once, since I'm adding to the amount of time that it takes to access that element within it, I will know I'll know what to divide by. I'll be able to divide by xlist sub index to find out the average access time for that element. Okay, so when I go to plot this, I plot the sequence, give the sequence a name and a color, and then I plot the data points. The x is going to be, in this case, the size of the list that I'm working with here, and then this is the average access time for that, I'm sorry, this is the location within the list where I was accessing the element, and this is the access time, the average access time for accessing an element at that location within the list. So again, sequence and then the slash sequence, and then the slash plot is important right at the very end. Gives me the total amount of time. Okay, so let's run this. Okay, so it's finished. I had to let it run for a few minutes here. I cut it out of the video, but it's finished now. And as a result, when I go and look, I have this list access timing.xml that's in the directory where the program resides, and I can go ahead and plot that now. So just type plot data at the line here and click on the window so that you get the menu. It doesn't show up right away on a Mac. It should be right on the window for a Windows platform. And I want to get into the Dropbox, I guess, in this case, classes directory 160, and it's this list access timing that I want to look at. And I get this nice plot that shows me how this performed on this system. So the red line is the average access time versus list size. And what that shows me is that at 1,000, it takes relatively the same amount of time to access elements within a list within a list of 1,000 elements, I guess, as it does to access elements in a list of 200,000. So it doesn't. The list size does not change the amount of time that it takes to access an element within the list, the average access time within the list. And that's indicated by this relatively flat line. It's not going to be perfectly flat because this is an experiment and there are other things running on this computer while this experiment is running. So there's bound to be a little bit of up and down. There's a couple of spikes on the blue one. This is the access time distribution. So this is in a list of 200,000. How much time does it take to access an element here versus an element down here in the list of 200,000? And is it any different within the list for one list of 200,000 elements? Now these two spikes, that happens occasionally. Something else was probably going on at the time that we did that list access, and it quit processing. The Python program for a little bit, went off and did something else, and then came back. But these 2 points, these 2 data points, are anomalies, and we don't really need to be concerned about them. They're not due to the Python program, other than maybe perhaps garbage collection was running while we were timing for those 2 data points. Okay, so we're going to be using this quite a bit to understand the complexity of our programs and get an idea for what's going on. We'll also talk about the complexity from a more theoretical standpoint and understand exactly why these programs take the amount of time that they do. But this is an interesting experiment to do on lists, because one of the fundamental operations that we are going to do is access elements within a list and be able to store values within a list. And we need to know that the size of the list, that's the red line, does not affect how long it takes to access an element, any element within a list, nor does it matter where we access an element within a list, and that's the blue line. So if we access an element in a list of 200,000 all the way down here, it's exactly the same amount of time that it takes to access an element down close to 1,000 here. So this is called big O of 1 complexity for both of these operations. Big O of 1 because it's constant time complexity independent of the data size. It's a straight line across, and that indicates big O of what's called 1 complexity.